So this method didn't work, right, for this example. But can you make a comment about the stability of this equilibrium point 0? How would you assess the stability of 0 for this system? Graphically, good. What would you do graphically? So I think you would draw it for x and x dot, right? How does it look like? Cube? Is it something like this? Okay. Then what is my velocity on the right-hand side? Positive. And then here, it's negative. So it seems everything is trying to escape from this point, right? So it's unstable. But the previous method didn't give us the correct answer. So the motivation, this is...
I have a question. So I kind of understand, but
yes.
It makes sense when you're saying it's velocity. What if x dot is something else than velocity?
Actually,
I don't lack the intuition why it means in general where x dot
yes.
has the derivative.
Yeah, because if I have more than one, so if I have a higher order system, like fourth order system, I'm trying to write the states in a way that I will always have the velocities on the left-hand side. So if I have 4 states, I'm just writing x1 is equal to x1 dot is equal to x2, x2 dot is equal to x3, x3 dot is equal to something, and then x4 dot is equal to something. So on the left-hand side, I always have the velocity. This is the representation of actually state space. So we are writing x dot is equal to ax plus bu. So this one could be n multiplied n by n, and no matter how big n you have, on the left hand side I have only x dot. It's a state vector, right? So it's mathematically correct to talk about the velocity. Okay, so this is unstable, and when would it be stable, do you think? If I have added this, it would be stable, right? Okay, so we will come back to this later on. Now we will talk about Lyapunov's direct method, and I will try to talk about stability concepts a bit more. Again, we will talk about one word, as I said, only stability today. Can I switch back to the laptop?
Yep. I did, I think,
oh.
in this tool.
Yes. Oh, great. Yes, okay, perfect. So let's talk about Lyapunov's direct method. I will introduce positive definite functions and Lyapunov functions to you. And then I will talk about equilibrium points, local stability, global stability, and then some remarks about Lyapunov functions. This is a very strong tool, okay? And you can use it for many purposes. Analyzing the system, designing a controller, and so many controllers, like sliding mode controller and some other ones, they are based on this method. So, first, let's talk about this largest rope.
Lieverd, tomaten?
Not this one.
Ja, tomaten.
Nederland op zijn lekkerst. Nu vers bij je thuis. Flexibel studeren
Not
doe je
this
bij
one either.
NTI. Schrijf je voor 1 juli in op nti.nl.
Yeah, internet connection. Ederom is a bit slow. Yes, please.
Flexibel studeren doe je bij NTI. Schrijf je voor 1 juli in op nti.nl.
Oh yes, this is a swing that I like in the US. So so people are doing crazy things. Yeah, I would never do that, but let's see what's happening.
Alright, kick back, relax, and grab yourself a beverage. If you wanna just bounce to my lyrics,
Would you do that?
the evidence, as they say, is in the pudding. So show me the money like my name was Cuban pudding. It ain't fool's gold, it's gold, fool. Can't stop, won't stop, keeping it old school. Big Spoon is my Nante plume. I keep it popping like a needle in a new balloon. And if you don't know by now, then you need more schooling. Let loose, kid. Get
Looks like it is.
got more flavor than I know what to do. It's to get your hands up if you're part of the movement.
Okay, but
To the bump, to the baseline.
I mean, what do you expect? What will happen in the end?
Yes, sirree. You know
Okay.
my steez. I stay fresh
Yeah,
to
they will
death,
reach a
turning
stable
through
point.
breeze.
So the energy will be dissipated all the time. This is our, I mean, no matter what's happening in between, eventually we know what's going to happen in the end, right? So the energy will be lower and lower. The kinetic energy will be lower and lower. Actually, this is more or less where the Lyapunov started thinking.
Hello,
He
nurse. Let
thought
me burst on this verse.
an
I
energy-like
rap steady, but I
function.
never rehearse.
And then he
every
started
verse
his
I work is
analysis.
right on the money. Yo, I got more raps than a mummy.
Okay, you can
This
see
beat a
the
boogie
rest
that
of the
jumpstarts
video.
your ventricles, strapped on the track like tentacles.
So what is it going to happen in the end? The energy, the kinetic energy will go down. Okay. Yes. So the fundamental physical observation is this. If the total energy of a system is continuously dissipated, then the system must eventually settle down to an equilibrium point. So if I'm sure that the energy is being dissipated over time, I'm also sure that it will settle somewhere, right? So I'm sure about this physically. And the mathematical extension of the physical observation, this physical observation, is the Lyapunov's direct method. Not indirect, but direct method. So the question, can we examine the stability of a system by eliminating the variation of a single scalar function? So there is the nonlinear system and set of equations. And then you create another function which is totally independent of the system equations. And then you evaluate this function, the change of this function over time, and then if the value of this function is going down all the time, then you say the system is stable. And this function looks like the energy, right? So if the energy is going down, then the system is going to be stable. So it's something like this. So you define such a function. I mean, there are some rules about this function, of course, but let's think about it in 3D. You find this function, and then once you are on this function, if you are always going down, like a cup, or inverted cup, let's say, you will always go to this direction and you will settle down somewhere here. So this is a mathematical function, but it looks like an energy function. That's why it's called energy-like function. And if you can show me that the derivative of this function is always negative along the trajectory, then it will mean something to me. The function may be considered as an energy of the system, total energy of the system. Actually, it could be defined as literally the energy of the system, if you have a mechanical system or electrical system, but it doesn't have to be. You can also suggest entirely another function. It's not energy, but it will be energy-like function. So let's consider this system. It's a simple mechanical system. Is it linear or nonlinear? Yes? Linear, nonlinear? Who says linear? No one. You have x dot multiplied by absolute value of x dot, x cubed, obviously not linear function, so it's a nonlinear function. And then you have an interesting nonlinear damping. It's like x dot multiplied by absolute value of x dot. And then you have a spring term. Spring term is also nonlinear. Okay. How do we get these models is another story. We are not focusing on modeling, but let's assume that this model is given to you. and then you're trying to analyze the system. So if the mass is pulled away from the natural length of the spring and then released, let's say, if I just take it here and then leave it, is it going to be stable or not? Is it going to, the energy is going to go down over the time or not? This is our question. So can we find the general solution of this nonlinear equation? Or, instead of it, can you linearize it and then make the analysis? The first one is unfortunately not available because the closed-loop solution of nonlinear functions are mostly, not easy to get, or sometimes it's not possible to get. Right? Most of the time it's not possible to get. So the first method is not going to work. Can you linearize? Yes, you can. You can make you can use the method that we saw in the first lecture. But we have also seen that there are some drawbacks of this method. And then the linear approximation, if you find the linear approximation of this system, it's going to give you marginally stable case. This is not true answer, like the example x cube. So alternative solution is, if we examine the energy of the system, if we write the energy of the system and try to analyze the energy of the system, then it can give us a better result. Let's write the energy of the system. So the total energy is the addition of the kinetic energy and the potential energy, right? So this is the kinetic energy of the system, and this is the potential energy of the system, the overall mass. And then if you write it like this, you can calculate the integral of this one. You have this term again, and then the total, you can have now the total energy of the system. And zero energy is the equilibrium point is both the position and the velocity is equal to 0. So this is your equilibrium point. So where the mass is stationary in the beginning. So this is your 0 point, right? And the asymptotic stability implies the convergence of the mechanical energy to 0. So I will define this term mathematically in a little bit better way. But we can say the asymptotic stability is a special kind of stability, indicates that the overall energy of the system is going to go to 0. Because it might converge to somewhere else as well. If it is converges to 0 specifically, then I call it as asymptotically stable. And instability is related to the mechanical energy of the system. If the energy of the system goes to infinity, then I say, okay, the system is unstable. Yeah. So the relationship in the previous slide indicate that the value of a scalar quantity, the mechanical energy, indirectly reflects the magnitude of the state vector. Therefore, the stability of the property can be characterized by the variation of the mechanical energy of the system. So the stability of the system is directly related to the energy of the system. If the energy is going up, the system is not stable. So now I have started making a connection between the energy and the stability. The next step is going to make the same connection with an energy-like function and the stability. So this is the first step. Okay? So what is the rate of the energy variation during the system's motion? How do you find the rate of energy? How do you find that whether it is going up or going down? What would you do? You would find its derivative, right? So if the derivative is negative, then the energy is going down over the trajectory, right? So we can do it. Let's find let's differentiate this energy function. When we differentiate this energy function, you have m x dot x double dot, and then you have 2 like k0 x dot, etc. And if you just calculate this function, suddenly you have this. So if this function, okay, this function is in any case positive, right? Absolute value of x dot. This one, if it is positive, the friction coefficient, if it is positive, this function, the derivative of this function, right? Time derivative, it will always go down. So the energy will be dissipated. Is it in line with your intuitions? Friction coefficient. If the friction coefficient is positive, the system is stable. So what did we do in this slide? We have written the energy of the system, calculated the time derivative, and then seen that the time derivative is always going down. So if something is always going down, eventually it will settle to 0. So then the system is stable. So this is the first step of Lyapunov's direct method. So the result, equation above, says that the energy of the system is dissipated by the damper until the mass settles down. Where is it going to settle down? At 0. What was expected. So could you get the idea of what we are doing? Any questions? Who wants to summarize what we have done? Yeah, is there anyone who wants to summarize? What did I do? First, I have written the nonlinear system equations. Then I have written the energy of the system, potential and kinetic. And then I have calculated the time derivative of this. And when I calculated time derivative of this, I have seen that it's strictly negative. So if the change is strictly negative, then something is going down, like the energy is dissipated. So then the system is stable. This is my comment. What was Lyapunov's indirect method telling me? It was telling me that the system is marginally stable. But actually the real answer is not marginally stable, it's stable. So Lyapunov's indirect method doesn't tell me the correct answer all the time. Okay, this was the beginning of everything. So let's continue. Lyapunov's direct method is the generalization of the concepts of the nonlinear spring mass damper system to more complex systems. So this system is a bit easy because you can write, again I have used the word of easy, because you can write the kinetic energy and the potential energy of the system, but you can't do it for all systems. Imagine that you have super complex system, you cannot write it, right? So you have to have a better solution. So then the basic procedure of Lyapunov, he said like, okay, then why don't we create another function, like an energy-like function. It's not energy, but it's going to be energy-like function. And then we examine the time variation of the scalar function. So you do the same thing again. Another function, find its time derivative, and then analyze it. If it is lower than 0, the time derivative, then you can say, oh, the system is stable. This is the beginning. Then we can make comments about the stability of differential equations without using the difficult stability definitions. Or we don't need the explicit knowledge of the solutions. We are not solving the dynamic equation. We are not linearizing. We are not doing anything. We are just defining another function, energy-like function. But then the question is, okay, how are you going to define this function? Who tells you what function is going to give you the correct result? That's the main drawback of Lyapunov function, because you don't know the correct Lyapunov function. Different Lyapunov functions can give you different results. So that's why we call it as candidate Lyapunov function, because every Lyapunov function you suggest is a candidate function. You don't know whether it is the correct one or not, right? So if one of them doesn't work, what you're doing, you suggest another one. And if it doesn't work, you suggest another one. It looks like maybe a little bit weird to you, but there is no other method that you can use, actually. So he suggested this method, and this is the only method that we can use. Okay, let's do it. So what comments can we make about the equation below? This is an energy of the system. What do you see here? What comments can you make?
It's always positive.
It's always positive is a great answer. It's always positive. Makes sense because it's energy, right? Energy cannot be negative. Okay, it's always positive. So this function is strictly positive unless both state variables x and x dot are equal to 0. So it has a global minima at the origin. Otherwise, it's positive all the time. Okay? And the function is monotonically decreasing when the variables x and x dot according to the system dynamic equation. So this function is always decreasing along the trajectory. So there are two rules, right? Strictly positive, and then it should decrease over the time. So then this is giving an idea of what kind of functions can I propose. For instance, if there is one variable, x, my Lyapunov function, can my Lyapunov function be x? Vx is equal to x. Can I propose something like this? Not really, because it's not strictly positive. So I can propose something like x squared, 1 over 2 x squared, x to the power of 4, x to the power of 6. So it will be strictly positive. So conditions of this function. So the Lyapunov's function, the first property is formalized by the notion of positive definite functions. So we have to understand what is a positive definite function then. Then the second property is formalized by Lyapunov functions. So if a function is positive definite and its derivation is going to 0, or let's say its derivation is smaller than 0, then it's a Lyapunov function. Let's see. Okay, this is a formal definition. A scalar function Vx is said to be locally positive definite by, okay, the bold ones show that it's a multidimensional signal, right? Because I don't know whether my system is scalar or not, so I'm using bold term here. Vx is equal to 0, and then in a ball, the ball is BR0, capital 0. When x is not equal to 0, Vx is going to be greater than 1. And this property is going to be held for the whole state. If this is held for the whole state space, then Vx is globally positive definite. It's the formal definition of this sentence, actually. So I'm saying if Vx is greater than 0 at a certain ball, BR0, it's locally positive definite. If it is greater than 0 for the whole state space, then I say it's globally positive definite. But the rule is, when x is not equal to 0, Vx is going to be greater than 0. It's the same for energy. Okay? For example, the mechanical energy of the system, the spring mass damper system, is satisfying this condition because this function is equal to 0 when x and x dot is equal to 0, and otherwise this system is always positive because this is positive, this is positive, this is positive, this is positive, and then this is positive as well. So its function is always positive, globally positive definite. Okay, a few notes about the positive definiteness. Let's elaborate what is positive definite function. The definition in the previous slide implies that the function v has a unique minimum at the origin. Yes? So the function has a minima at the origin, and it's unique minima, right? So this is the definition of positive definite matrix, positive definite function. I said positive definite matrix because we will also talk about positive definite matrices as well. So it has one unique minima at origin, at 0. And given any function having a unique minimum in a certain ball, we can construct a locally positive definite function simply by adding a constant that function. What I mean is, if your function is, I don't know, Vx is equal to x squared minus 2, you can add 2 and then it's going to be positive definite. So if it is lower than 0, and then if it is a unique minima, you can add a simple constant and then you can make it greater than 0. And then the function is going to be shifted, of course, in this case. But the time derivative is not going to change. So x squared minus 2 and x squared, from the time derivative point of view, they won't have a big difference. So the result is not going to change. It's something like this. So you have one energy-like function, right? And then Vx is typically corresponds to a surface looking like an upward cup. So it's like a surface in 3D. And then the lowest point of the cup is located at the origin. So this is your origin. And in this case, your energy here is greater than your energy at V2, and it's greater than your energy at V1. So your energy is going down. Positive definite matrix. Again, a few concepts related to positive definite functions. So Vx is negative definite if minus Vx is positive definite. Correct? Is it like a complex sentence? Imagine that minus x squared. So if minus x squared is positive definite, which is x squared. So then you can say minus x squared is a negative definite function. I mean, it's the dual definition of positive definiteness. Okay, if the function Vx is positive semi-definite, then the function V0 is equal to 0, but Vx is greater than equal to 0. What is the difference here between positive definiteness and positive semi-definiteness? Yes?
Can be 0 at other places?
It can be 0 at some other places as well. So it can be 0 at multiple locations, right? So if this is the case, then we call this function as positive semi-definite function. Okay? And this function Vx is negative semi-definite if minus x is positive semi-definite. Lots of definitions here. But I think you understand what positive definite is. And the prefix semi is used to reflect the possibility of V being equal to 0 for when x is not equal to 0. This is exactly what you said. It can be 0 when x is not equal to 0. Okay, so positive definite, are you clear about positive definite metrics? Vx is greater than 0, and there is only one minima at 0. Yes, this is the positive definite matrix. So when you propose a Lyapunov function, you have to satisfy these rules. It has to be either positive, it has to be positive definite. Okay, can you make comments about the positive and negative definiteness of the following functions? Let's discuss only two of them, and I leave the answers to you for the rest of them. So do you think this function is positive definite?
Yes.
Yes. And how about this one? Negative definite. Okay, I leave the discussions to you for the rest of the two. Positive definite or not. Okay, a nonlinear function, I think I have given this definition to you, is said to be autonomous if f does not depend explicitly on time. So x dot is equal to fx means I am defining the trajectory based on my state. Don't get confused about something that the state depends on time. Of course, state depends on time, but I mean state changes with time, but it doesn't explicitly depend on time. So I don't have f comma t here. So I have only fx. So this is an autonomous system, the definition of autonomous system. Otherwise, the system could be non-autonomous. For example, the electrical circuit is an autonomous system, but if I write resistance value, if the resistance value changes over time, then it wouldn't be. Okay. But most of the systems that we are going to deal with is autonomous systems. And assuming that Vx is differentiable, its derivative with respect to the time can be found with this chain rule, because V is doesn't depend on one single variable. It has several variables, right? Depends on the number of states. So you have more than one state, then you will just use the chain rule to find its derivative, okay? So the definition, another definition is, if in a ball BR0, this ball is, I say ball, but it's just a set, let's say, also a local invariant set. In this ball, if the function V is positive definite and has continuous partial derivatives, and its time derivative along any state trajectory of the system is negative semi-definite, Vx is said to be Lyapunov function for the system. It's the whole necessary and sufficient condition. Let's just read it. It's going to be positive definite. It will have continuous partial derivatives, and then its time derivative is less or equal than 0, then this system is Lyapunov function. Something like x squared, x1 squared plus x2 squared. I mean, you can suggest infinite number of functions. Yes?
So this is just a clarification. So this last condition is just stating that the energy has to decrease over time, right?
This is the necessary and sufficient condition for choosing my Lyapunov function.
Yeah,
This rule,
in the last fragment,
yes, in an indirect way, yes, it's related to energy. This condition says, for instance, you can't choose x minus y as a Lyapunov function, because this doesn't satisfy these rules. It has to be a certain function. Okay, now so why did we see all these definitions? Positive definiteness, Lyapunov functions, like all this stuff. Actually, we are trying to come to a conclusion, because my ultimate goal is to make a conclusion about the stability of the system. So if there is a relationship between this function and the stability of the system, that's great. Then I can use it as an analysis tool for the stability. So there exists a relationship between Lyapunov functions and the stability of systems, right? Otherwise, I wouldn't show all these slides to you. Imagine that I have spent half an hour and then in the end I said, okay, there is no relationship. I just showed them for fun. You wouldn't enjoy. Okay, definitely there is a relationship between the stability of the system and these Lyapunov functions. Such theorems have local and global versions. So you can make comments about the local stability, global stability. There are slight changes in these theorems. I will show you one by one. So I will show you one theorem, local stability. Okay, this looks like complex, but it's not. It's so easy. So if in a ball is just an invariant set, there exists a scalar function Vx with continuous first partial derivative such that Vx is positive definite, if Vx is positive definite, and V dot x is negative semi-definite, it's semi-definite, and within this ball, a certain region, then the equilibrium point at the origin is stable. Good conclusion. Great conclusion, right? So as you see in this theorem, I haven't solved the system. I haven't solved the output of the system. I haven't analyzed local stability. I haven't done anything. I have just defined a function and said, if this is positive definite, if V dot is negative semi-definite, then it is stable. Isn't it nice tool? Like you make a comment. Okay, let's talk about this system. Is it linear or nonlinear? What do you think? Yes? Nonlinear. And nonlinear term is the sine of theta, right? It's not a linear term. Okay, what comment can you make about the stability of the system? Actually, you might say, in the beginning of the lecture, I told you several times, we can't talk about the stability of the system, so how come you can ask us the stability of the system? So these questions for nonlinear systems, implicitly it is asking the stability of 0, 0 to you. So that's why I'm not always writing what is the stability of origin, what is the stability of origin, but these questions are always asking you the stability of origin. So what comment can you make about this system? So we can consider a scalar function, Vx is 1 minus cosine theta. This function doesn't have any relationship with the system function. It's totally independent, right? Doesn't have any, it's just another function that I write. What are the rules? It has to be positive definite. Okay, is it positive definite? Let's check. This is positive. And what is the minimum value of this function? 1, right? Or let's say maximum value of this function. So this is going to be change between -1 and +1. So if it is -1, it's going to be 2 plus number, so it's going to be positive. If it is 1, then it's going to be 0 and it's going to be positive again. So this function is definitely positive definite. So it's a candidate Lyapunov function. Is it complex? Okay. And then you can say like, okay, why did I write 1 minus cosine theta? I want to write, okay, why did I write this over 2? I want to write theta dot squared. It's okay, you can write it. So it's going to be another Lyapunov candidate function. If you say, I don't want to write 1, I want to write 2, it's okay, you can do it. As long as it's positive definite, you can suggest any Lyapunov function you want. Yes?
This function is only positive definite in a certain region, right? From minus pi to plus.
Okay, it might be if it is like this, we will have one set of conclusion. If it is not like that, we will have another set of conclusion. It's going to be the last slide of this presentation. I will summarize everything. So we are now talking about the local stability, okay? So this is positive definite for sure. What was the second condition, necessary and sufficient condition? Derivative should be semi-definite. Then my conclusion is going to be stable. So let's see whether we can do it or not. Okay, what is V dot? V dot is theta dot sine theta, theta double dot theta. It's here, right? Minus sine, minus minus positive, sine theta, theta dot, 2 times theta dot, theta double dot. 2's are cancelled. And then you have this function, V dot. Okay? And then this function is smaller than theta dot square. Don't ask me why. This is a typical trick that we use in control theory in our proof. So when I try to show that a function is smaller than 0, I just choose a bigger function of this function, and then I show that the bigger function is smaller than 0. Then in an indirect way, I have shown that the first function is smaller than 0. So I'm using this trick here. And then if you just carefully look at this equation, you will see that this function, so this function is bigger than this function. And then if it is smaller than 0, this is going to be smaller than 0. So this is going to be theta dot squared. Theta dot squared minus theta dot squared is definitely smaller or equal than 0. So then we have got the second necessary condition. Vx is positive, v dot is negative semi-definite. So then I can say, we can conclude that the origin is stable equilibrium point. The system is stable. And then, with this Lyapunov function, we cannot draw any conclusion about the asymptotic stability of the system, as Vx is only negative semi-definite. Okay, let's now talk about stability and then asymptotic stability, okay? Great. So let's say I have a region here. It's something like, again, an invariant set, right? And then my trajectory is starting from here, and then it goes into this place, and then it does something, I don't know. But it never goes out from this region. This stability is defined as a Lyapunov sense of stability. The other one is asymptotic stability. So when this is origin, if this trajectory is making some movements and then ends up at 0, this is asymptotic stability. Okay? So there are two different types of stabilities in nonlinear systems. And linear systems, now you're going to be confused more. Linear systems, if they are stable, they are both Lyapunov sense of stable and asymptotically stable, because linear systems will always converge to 0, 0. But nonlinear systems, they don't have to be. Okay? So the first one is Lyapunov sense of stability. Second one, when it goes to 0, it's asymptotic stability. There are more definitions. Later on, we will talk about them. Let's confuse you slowly. Okay? So this theorem says, this function says it is Lyapunov sense of stable, but is it asymptotically stable? So is it going to 0 or not? It cannot make a comment, because it's less and equal than 0. So I think now you will get an estimation of what am I going to do as the next step. So I will try to write the necessary and sufficient conditions for asymptotic stability. Yeah? So we can modify our definition and then we can write it. Any questions so far? Okay. Again, summarizing, what did we do? We have defined a function, Vx, we have calculated V dot. V dot is smaller or equal than 0, then we said the system is stable. This is the procedure, 3-step procedure. Okay? So, how about the stability of this system? You can use the same comment, you can use the same method that I used in the previous lecture. But it has several steps, right? Find the Jacobian, find the local local equilibrium points, make the I mean, there are several steps. But here is, we can make a comment in one step actually, with Lyapunov functions. So then they say, okay, I define a Lyapunov function, x1 squared, x2 squared. Can I define this function as a Lyapunov function? Yes, because it's positive definite. I can do it. So it's no problem. So is the function is positive definite? Yes. What is the second step going to be? I have to find V dot. And V dot is equal to 2x1, x1 dot, 2x2, x2 dot. And x1 dot and x2 dot here, where are they going to come from? They are going to come from here. So find V dot, and wherever you see x dot, write this equation. Wherever you see x2 dot, write the second equation, and you will have a set of equations, x1 and x2. And just try to analyze it. Okay, let's do it. V dot is this one. And if you make some play with the numbers, you are going to get this one. So this is positive. This is also positive. Okay, this is not important. Minus 2 means it's less than 0. So V dot is negative. Okay, V is positive, V dot is negative. Again, what comment did you make? We can conclude that the origin is stable equilibrium point. So, did you see the strength of Lyapunov's method? Normally, I spent around 15 minutes to make a comment about the stability of origin in the previous method, but in this one, I did it only in 2 steps. I defined V dot is negative, stable. So it's very straightforward. I mean, it is easy if you know this function, of course. If you write another function here, maybe you may not have the same conclusion again. Then what you do is you suggest another one. You suggest another one. That's the weakness of the method. Okay, so then we can conclude that this is a stable equilibrium point. And using the Lyapunov function above, we can say that the origin is asymptotically stable because Vx is negative definite. So now you have a slightly different version of Lyapunov sense of stability. If Vx is smaller or equal than 0, you say locally stable, but if it is smaller than 0, then you can say asymptotically stable. So now in our definition, we have made a difference between Lyapunov sense of stability and asymptotic stability. And it just depends on this, whether it is equal or smaller or it is smaller. If it is smaller than 0, you have asymptotic stability.
Sorry?
Yes?
So we only need to analyze this for the values of x1 and x2 around the origin.
Yes. Because the question is this, like what comment can you make about the origin? This is the question.
Because otherwise the function can get one.
Yes. Yes.
Thanks.
Okay, so Vx is negative definite. V dot x is negative definite. So then it's asymptotically stable. Okay. So this is local stability definition, right? So what is the global stability definition? How can I say that this system is globally stable? So not an invariant, small invariant set, but for the whole state space. How should I modify the theorem? So in order to write the global asymptotic stability of the system, you might say that the ball that you define, because we were defining the function within the ball, you might say, okay, change the ball to the whole state space, and then the theorem will be valid for global stability. Actually, this is necessary but not sufficient. We need one more condition. Of course, you need to do that. You have to define a function which is It's going to be valid for the whole state space, not within a small ball. Then additional condition for V is Vx must be radically unbounded. In other words, if Vx goes to infinity, if x goes to infinity, then you can say this is globally stable. Either globally Lyapunov stable or globally asymptotically stable. And our function x1 squared plus x2 squared, do you think it is unbounded? Yes or no? x1 squared plus x2 squared. If the norm of x goes to infinity, x1 squared plus x2 squared go to infinity, right? So this condition is satisfied in our Lyapunov function. Then I have another theorem for global stability. First, positive definite, V dot is negative definite. If V goes to infinity, when the norm goes to infinity, then I can say it's globally asymptotically stable. So now I have made one more step. Lyapunov stable, asymptotic stable, globally asymptotic stable. So the third condition is we should go to infinity as x go to infinity. Okay, global stability. And if the derivative of Vx is locally negative definite, then the stability is asymptotic. So when I say Vx is negative definite, not semi-definite, but it's negative definite, then I can say the stability is asymptotic stability, not Lyapunov stability. So because it could be smaller or equal, or it could be smaller, right? If it is smaller, I can say it's asymptotic stability. So I have made comments, right? Locally asymptotic, locally Lyapunov sense of stable, locally asymptotic stable, globally Lyapunov sense of stable, globally asymptotic stability. And all of them have some similar conditions, but they are, I think these conditions are somehow intuitive. After some time you get used to these conditions. So let us study the stability of this system. X dot is equal to Cx is equal to 0, where C is any continuous function of the same sign as its scalar argument. So x Cx is greater than 0 for x is not equal to 0. I mean, this is the mathematical function given to you, right? We don't know the physics behind it, but we know that the function will have the same sign of its argument, x, Cx. When you multiply, it's going to be positive. So if x is negative, Cs is negative, x is positive, Cx is positive, so it's going to be always positive when you multiply them. So the question is, what comment can you make for the stability of the system? Can we define the stability of the system? So let's just do it. Oops. Okay. Is your brain too hot right now? Okay. Consider the Lyapunov function, Vx is equal to x squared. Is this function positive definite? Yes. Is this function unbounded? Yes. I think now you are now understanding where am I trying to reach. I'm trying to reach a global stability comment, right? So unbounded, and then it's positive. So now I need to show V dot. How is V dot? So V dot is equal to 2x x dot, and then 2x x dot is equal to minus 2x Cx, and this is going to be always the same sign. It's given in the question. Then this system is, V dot is negative, sure, okay? So V is positive definite, V dot x is negative definite, it's given to us. And then V goes to infinity as x goes to infinity. Then what is our conclusion? Then this system is globally asymptotically stable. If it was smaller or equal to 0, I would say it is globally Lyapunov sense of stable. If it was locally, then I would say locally. Okay? So this is the strongest definition, globally asymptotically stable. So my question now for you, now we came to the question that I asked you in the end of the previous lecture. X is equal to minus x cubed. Can you show the stability of origin with a Lyapunov function? Do you have a pen and paper? Can you try a few functions? Okay, just write v, of course positive definite, then write v dot, put it here, and make a comment. I give you a few minutes, because you are so smart, you can solve it in a few minutes. Just try. Who is stronger in maths? Who has a conclusion? Yes? What is your conclusion?
Yes, it is globally asymptotically stable.
You say it's globally asymptotically stable. Okay. What is your Lyapunov candidate function? Sorry? X to the power of 4. Oops, just a moment. I did something wrong. X to the power of 4. So x to the power of 4 is definitely unbounded and positive definite. So you satisfy the first condition. And then you calculated v dot. What is v dot? 4x cubed x dot. And then what did you do next?
Substituted the dynamics equation.
Yeah, 4x cubed x dot. Then it's, what is it equal to? 4x cubed multiplied by x to the power of 3. So the end result is minus 3x to the power of 6, right? Something like this. Okay. So x to the power of minus x to the power of 6 is negative definite. So then your conclusion is globally asymptotically stable. Actually, that's true and that's the correct answer. You can come to this conclusion using another Lyapunov function, if you can. And then geometrically, I can say, by using the Poincaré's method, I can say it's globally asymptotically stable. Yeah, it's the minus x cubed, right? You can make the same analysis here. How is minus x cubed? Is it like this? So it's positive, it's negative, this point is stable. And it's globally stable. So then your conclusion makes sense. It's in line with Poincaré. And then this function, let's not do it, but you can define this slightly different. Okay, you have to define something with related to sine and cosine, right? But the story is the same. Propose something positive definite, find v dot, substitute here, and then see. Let's say you choose a Lyapunov function, and then you have substitute here, and then there is no result about the positive definiteness. What are you going to do? The function is something 1 minus x squared. I mean, it could be negative, it could be positive, it could be 0, so there is no conclusion. Like, in the end, what are you going to do in this case? Sorry? Yes, you will just say that I can't make any comment, I pick up another function. And then conclusion, let's say, is neither positive definite or negative definite. Then you can say I can't make a comment, I pick up another function, another one, until infinity. And that's why the nonlinear control and chaotic system exams are too long. We had exams when I was a PhD student, starting from 9 a.m. until 7 p.m. And the lecturer was bringing us some tea, coffee, and some bagels. And then we were solving the question for 10 hours non-stop. And then in the end, we were delivering 20 pages of solutions. And because there is no formula, closed formula, how can you reach the result, right? So you sometimes try and see. It's the same with other methods as well, like sliding mode control. Which control method should you propose? And then the system will be stable. It's just with trial and error a bit. Okay, so you can suggest another Lyapunov function and you can make a comment about this. How about this one? Again, you can linearize the system, but we don't like it. Okay, so we can make about the stability of the system. I choose a Lyapunov function, x1 squared, x2 squared. I think you have a little bit, after a few examples, you have a little bit feeling, right? How should it be? It's either squared, or to the power of 4, or sometimes we have sometimes 2 here, or it is sometimes like 1 minus cosine, 1 minus sine. So after seeing like 10, 15 examples, you have a feeling, like how should it be? So this is a typical Lyapunov function, x1 squared, x2 squared. So let's just, if you just find the 2x1, x1 dot, 2x2, x2 dot, and then substitute here, then this function is going to be this. 2 minus x1 squared, x2 squared squared. This is definitely negative, right? Negative. So v is positive definite, because this is positive definite. Second is negative definite, so this is negative definite. And then Vx goes to infinity, x goes to infinity. Then you can say it's globally asymptotically stable again. So note that the globalness of this stability result also implies that the origin is the only equilibrium point. This is the natural result, right? If origin is globally asymptotically stable, then there is no other stable point. Yeah, because otherwise it could be contradiction. So then this shows that this is the only equilibrium point in the system that is in the system, right? So it's globally asymptotically stable. Okay, so now I'm going to show you all our results in one table. So if V is positive definite matrix, L means like locally. And then if V dot is positive semi-definite locally, then your result is the system is stable. Weakest definition of stability. Weakest definition of stability is here. It goes to a region and then it doesn't go out. We have no idea whether it is global or local, whether it is going to 0 or not. We have no idea. It's the weakest definition. So line by line, we can make it more and more strict. The second line says if this is decreasing over the time. And if it is locally, again, this is uniformly stable. I will not talk about this one. And if it is locally positive, positive definite matrix, this is, then you can say asymptotically stable, right? Because this is, if it was positive semi-definite, it was stable. If it was not semi-definite but definite, then we said it is asymptotically stable. And if it is positive definite matrix globally, and then if it is positive definite matrix, then we can say globally asymptotically stable. We are more interested in this one. So we want our system, we want to define a Lyapunov function which is unbounded, positive definite, and then V dot is negative definite. Then we are going to say our system is globally asymptotically stable. We like this kind of stability.
So shouldn't that be NDF in the V dot?
Sorry?
Didn't you say it should be negative definite?
Which one?
V dot in third and fourth row.
Yes, there is a. I think it should be minus. Yes, yes.
No, but then it's less than 0 in the first row.
This should be less than 0. So either it is local, sorry, it's negative definite, or I should write minus V dot. It's the same story. After this slide, we have done the definitions of, so two different stability. Lyapunov sense of stability, asymptotic stability. Yeah, there is one more. Okay, so the last one is exponential stability. So let's say your system is globally asymptotically stable. So it means you are going to go to 0. But how fast are you going to 0? If you are going to 0 with an exponential function, then you say my system is globally asymptotically exponentially stable. So yeah, he did something like okay, and then a linear function, so a linear system, we said it's globally stable, it's globally asymptotically stable, right? Can I say every linear system is globally asymptotically and exponentially stable? You should say yes. Why? Because in any LTI system, your solution is, like in the first set of slides, c times e to the power of lambda t. So that means the solution is going to go to 0 with an exponential function. So your linear systems, again, just a summary, linear systems are, if they are stable, they are globally stable, they are asymptotically stable, they are exponentially stable. But nonlinear systems can be either stable or globally stable or locally stable. They could be Lyapunov sense of stable. They could be exponentially stable or not, right? So you see that the stability, yeah, this word, so we are still rotating around this word, right? So the definition of stability in a nonlinear system is not trivial. It's a bit complex. And then as a designer, when we design a controller, what do we want in our papers? We suggest first a control law, and in the end, if we say our controller is globally asymptotically exponentially stable, perfect. We like it. So we want our system to go to 0 with an exponential speed. Then it's great. We like it. But I hope you have got this idea of Lyapunov functions, how do we assess the local stability, and the differences between local and global definitions, and Lyapunov sense of stability and asymptotic stability. So overall, you may see my results here. Many Lyapunov functions may exist for the same system. So as a student, it's your task to find the correct one. For a given system, the specific choices of Lyapunov functions may yield more precise results than the others. So that means Okay, it's another weakness of this Lyapunov. So you choose a Lyapunov function, and then you make a comment, for instance. You say it's Lyapunov sense of stable. But who knows, maybe it's also asymptotic stable, and maybe you couldn't suggest the correct function, right? So there is a possibility that you couldn't suggest the correct function. So different Lyapunov functions may bring you different results. But of course, you want to find the strongest definition, which is globally and asymptotically stable. And for a particular choice of Lyapunov function, the conditions on V dot, if they are not met, one should conclude that a different Lyapunov function should be tried. So if the conditions are not met V dot, don't say that the system is not stable or is not exponentially stable. You can't make a comment. So it's not, so the rules do not work in the reverse direction, right? So if something happens, you have a conclusion, but not necessarily if you don't have this condition, you can make the other way around comment. I hope I have messed up your brains enough today. Yes, questions and comments. Or you can make, without any question, you can make a comment as well.
I'm still unable to grasp, like, what impact does the Lyapunov function have on the analysis, because it's not even like bounded in terms of we are not putting any limits on the system, but one Lyapunov function says the analysis is something and the other function has some other analysis. So there isn't a global analysis of a system, so I'm unable to grasp.
No, the conclusion says, so when you say, for instance, it's locally, let's say, your conclusion is locally Lyapunov stable. So this is true. I mean, you have concluded this. But you can't make one more step, whether it's global or not, if your conditions don't give you this result. This is what I mean. So you can't extend your conclusion to a little bit more strict definitions of stability. If your Lyapunov function tells you this is locally Lyapunov stable, then it's locally Lyapunov stable, full stop. No more. So in order to make a comment that is globally stable, then your Lyapunov function must give you this condition, necessary and sufficient conditions for global stability. It's the same for asymptotic stability. So what I say is, if you make a comment, you can't make it more strict based on your result, unless you see the result in your equation. So that's not that complex, actually.
But is it possible that for every system there might exist one Lyapunov function that will make it globally stable?
If the system is stable, globally stable, most probably there will be a Lyapunov function which is global. But the problem is whether you can find it or not.
Yeah.
Maybe there is, but you can't find it. Yeah. Yes, more questions?
So you said we have to search for these Lyapunov functions at, to the limit. But is there no ways to actually prove that the function like that does not exist, so that the system is not stable?
Oh, that's a great question. This is another story, but I mean, I have to go into really deep details of nonlinear control theory now. But let's keep our lecture on this.
One sentence.
It's difficult to give the answer in one sentence, but let's keep our case to there exists a Lyapunov function, and then I can make some certain comments like this. So if it doesn't exist or not, it's another story. So my comment is for you is just one word, stability. You have seen how different they are in nonlinear systems. Actually, all the concepts in linear systems, they have their counterparts in nonlinear systems. What is this, for instance? Controllability and observability. What does it mean in nonlinear system? It has completely different concept. There exists a similar concept, and then we talk about input-output stability. We talk about some different things. Then we go into different tools like Lie derivatives. Like all this nonlinear control world is totally different. But what you should know, whether you work in pure control or vision or SLAM or whatever for underwater vehicles, they are totally, as you know, they have nonlinear models, that you have to know that the concept is different for your linear and nonlinear models. Yes?
Thank you very much, Erdal, for this refreshing in my case. But I have one question, following up on Andre's question. So on a practical sense, when you need to find a Lyapunov function, are there any heuristics, ideas that you can use depending on the model of the system? How do you start looking for deciding that you are going to be using x squared, or now I'm going to introduce cosines or whatever in my function?
Yeah, I mean, actually I don't have any rules for this. So it's a little bit intuition, it's a little bit trial and error, but as we have seen 4 or 5 different examples, we have a more or less feeling, right? For instance, our colleague just chose x to the power of 4 because he has a more or less feeling, right? So he knows that it should be either x squared, x4, or 2 times x4, 2 times, and he didn't choose sine or cosine. Most probably he thought like the original function doesn't have sine and cosine, so why should I make it more complex? And then he didn't choose a multiplier because he thought maybe it's not needed for this function. But maybe if you see something sine, cosine, maybe you should also choose something sine and cosine. So there, I can say only there is some feelings, but no closed formula, unfortunately.
Are there any tools to generate these functions, or?
You generate it by yourself with your pen. Like, that's why we have control theory exams, that you will spend hours and hours in the class.
So maybe get a control book and start checking those that are suggested.
Yeah, that's true. So, okay, as the control engineer, we have only analyzed the system, right? We haven't designed anything, did we? But what is the ultimate goal? Ultimate goal is to design a controller. We didn't see any controller here. So, one step later in this topic, you will suggest a controller. And then you will write your control law into your system equations and show that your error is stable. So this is the controller design. So this was just analysis to understand. We haven't changed anything, right? Philosophers only tried to understand the world, but they haven't tried to change it. It's a famous quote from someone. Yes?
I had a question as well. When would you choose the direct method versus the indirect method? Because it seems like the indirect method can give some inconclusive conclusions.
Yes.
So why would you not always do the direct method?
Because it's more difficult to find the correct Lyapunov function with the direct method. It's stronger tool, but it's difficult, more difficult to apply. Indirect method is just straightforward, but it's not giving you the correct answer all the time.
And then when do you know when the answer is not correct?
It's always correct, sometimes it's inconclusive, right?
Yes. No. He says when to choose direct and when to choose indirect. I can say experience.
Okay. I think I lack a bit of experience, but thank you.
Yes. So when is our lunch break?
It was 10 minutes ago.
10 minutes? Oh my God. This is definitely a negative feedback. I got one more negative feedback. I don't remember the positive feedback, I remember negative feedback. He doesn't appreciate our break time. Something like that.
I'm going to ask the next lecturer if we can extend 10 more minutes and start 1:10.
Yeah, that should be fine.
It's fine.
Yeah.
If we reduce a bit the coffee break, or because we really need to finish at 4.
Yes. And if you want, I can make these slides available to you.
So, thank you very much. Erdal.
Thanks a lot.
Wow.